logic actually propagates through this OR and AND gate. Okay, so instead of, we can actually observe these nodes, and we can actually see that there is some logic we can actually put there, which directly changes our from this node to this node. Okay, so these change we have done, and we introduce a pre-charge MOSFET. So some of the, whenever the logic at this changes, it quickly pre-charges, and it charges this node instantaneously and allows to the fast speed of operation when division by 3 mode happens. So these are some of the improvements we have done. Then after the conventional architecture, there have been many papers they have actually also improved. So we compared with the most of them, and we what we observed that conventional architecture is the structure which consumes maximum power, and with the same D flip flops, with the same um, design, that is the same W by L ratios, by considering for PMOS and NMOS for all the designs with the same um, capacitance at each node, we calculated the power consumption by varying the input frequency, and we observed that the proposed architecture actually shows the 67 to and 69% power saving in division by 2 and division by 3 modes respectively. Also, it shows the 30% and 48% saving in the division by 2 or 3 mode in the PDP performance. Okay, so these are some numerical values. So the average power that we can get is 74 microwatt per gigahertz, and for 1110 for prescaler 2. Also, it shows less power consumption compared to the other architectures. Okay, and also the PDP performance, it some performance also improved at a 6 gigahertz when measured at 6 gigahertz. So these 2 by 3 scalars we embedded into the MMD architecture, and we did a post layout simulation, and at a different worst case corners here. Okay, and what we observed is when we vary the VDD from 0.8 to 1.2, we actually calculate a maximum frequency at which these MMD, proposed MMD, will operate satisfactorily. So when we saw at the FF corner actually gives around a 14.1 gigahertz, 14.2 gigahertz maximum operating frequency. Okay, and for TT corner it shows a 10.1 gigahertz, and for SS corner it shows 6 giga. Similarly, the power consumption is also checked at that frequencies. So the in the TT corner, the maximum power consumption is occurred, it is 3.5 milliwatt, whereas at a 10.1 gigahertz when BTT is 1.2 volt. Okay, it's then considering particular case like a supply voltage, considering 0.95, input frequency applied is 6 gigahertz. Okay, and with the process corner, we change the division ratios and found the power consumption, maximum and lowest power consumption. So when division is 8, we observe that the power consumption is 0.91, and when 127 is the highest division ratio, then we get a 1.6 milliwatt. Okay, so these are some of the papers where they have actually also implemented MMD with a different logics, and some of them are fabricated results. So we actually compared with our post layout results. Okay, so the CML logic actually operates at high frequency here in 65 nanometer, and but the power consumption is very high. Okay, the TSPC logic here at 65 nanometer, this actually shows also very good performance at high frequency, but the divisions are not continuous divisions, they have discrete divisions like only 64, 80, 96, 100, like this. But and in the proposed this work we actually compared at 6 gigahertz with a power consumption of 1.6 milliwatt, and when supply voltage was 0.95, and we actually got a very seamless continuous division from 8 to 127. So the conclusions uh, I have taken out some conclusions that the architecture is a programmable, can provide a programmable divisions from 8 to 127 with a TSPC logic, and the two prescalers are actually designed with a low power and high speed operation. The overall performance is like this: the power consumption is a 1.6 milliwatt, and highest power consumption and lowest is a 0.91 milliwatt, while they are operating at 6 gigahertz. Okay, at the supply of 0.95. Okay, and the main drawback is they have stack structure in the proposed design. So what happens, the propagation delay in the division by two modes slightly increases. Okay, also we cannot go the lower supply voltages like below zero point 0.8, as is as the logic doesn't let it to work properly. Okay, so that's all. For Thank you for your attention. Are like this. So we actually this